Hello everyone. So I hope I'm audible. I'm not very well today, so I might cough. So please bear with me today. Okay. So what I'll do now is uh, I'll show you the codes for genetic algorithm and local search and also simulated annealing for knapsack problem. So if you have not seen last day's class, then it might be a little bit difficult for you to understand genetic algorithm. Nevertheless, you can come back to these lectures whenever you have time and then revise and if you have any issue during that time, you can just you know uh, come back and we will talk about it. So first I'll share here. I hope my or voice is clear, right? And my screen is visible, right? My screen is visible. Let me check. Yes, thank you. Okay. Right. So what I'll do is, so this is the Python program which I have written. So you see, if you're not able to understand this, you can ask me questions and we will try to follow the steps which we talked about in our class. So for local search, if you remember, the point was to start with a feasible solution and then check its neighbors. So we will create neighborhood. So we'll start with a solution. I can show you some maybe pictures. So local search neighborhood. So the idea is something like this, and this will work. So you see, what is happening is we are starting with one solution. So this dot represents the starting solution, and this circle represents the entire neighborhood. So whatever point is inside this circle is the neighborhood. We will explore the neighborhood. If we are doing exhaustive search, then we will explore the whole neighborhood. Whichever is the best solution, we'll move to it. So over here it has expanded the neighborhood. It shouldn't be the case because this point where it is moving should be inside the neighbor. So this is what it is actually. So over here it has started and it is checking the first neighborhood, this neighborhood, and inside this neighborhood this is the best solution it is finding. So I hope you can see my cursor, right? So in this point it will check its neighborhood. So this second circle is its neighborhood, and in that neighborhood it sees that this is the best solution and it is moving from that solution to a local optima, and it has just expanded these points to make it very clear. But this point should be inside this circle because it is one of its neighbor. Okay, so this is what we'll do when we will try to code the local search. So, and we are talking about knapsack problem. So the representation which we have is we will have one list of numbers and each index represent items, right? So what I'll do is I will restart and clear all output. Okay, and let me run these first. I'll come back. I'll come back. So you see what I'm doing is I'm randomly generating. So these are the items. So I have 20 items, right? So what I'm doing is I am randomly generating items. So if I write items, so there are, so this is the first item which has a weight of 9 and value of 57. Second item weight of 5 and a value of 90, and so on and so forth. So there are 20 items in this list. So this is a list. The first element is the first item, the second element is the second item, and so on and so forth. Similarly, if I print capacity, so capacity is 50. So this knapsack, I have taken the capacity as 50, right? So I'll just delete this. and this item actually I'm randomly generating. So this is a way to randomly generate some items, or we can work with this example. If you're not comfortable, then we can work with this example. So over here we have 4 items, 1 2 3 4, and the capacity is 5. So either would work. So let me do with the bigger problem set, it will be better, right? So we are generating 20 items randomly. The weights are generated randomly from 1 to 10, and the value is generated randomly between 10 to 100. Okay, so this is the problem we have, and we have to pick items such that the total weight of the items does not exceed the capacity of the knapsack, right? And the value is maximized. Total value of the picked item is maximized. So what are we doing is, how will we represent a solution? So a solution will be a list, and it will have 20 numbers, right? So it will have 20 numbers. Each number will either be a 0 or a 1. So 0 represents that item is picked, and 0 represents the item is not picked, and 1 represents the item is picked, right? So if this one we are talking about, so the second item, because this one is at the second place, so the second item is picked, right? So we'll come to this code. So this code is actually a local search function which takes the input of items and the capacity of the bag, right? We will come to what this evaluate is. What it does is it checks how many items are there in the bag. So it takes n is equals to len items. It just means it is counting the number of items in the bag and storing it in this variable n. Now what it is doing is it is generating a solution. If you remember, to start a local search, you have to have a feasible solution. If you have a feasible solution, then only you can move to another solution. So we are just creating a random solution first, right? So this is a list with n elements, and these elements are randomly generated, and which will be either 0 or 1, right? But you see, when we are generating this random first solution, we don't know if this is feasible or not. So this while loop is actually doing what? It is generating solutions until we get a first feasible solution. Okay, so over here it is checking if the sum of the items is more than the capacity. Again, randomly generate some items. Again, it will, if it is not true, then it will do it again and again. Repeatedly it will do until and unless if it finds one solution which is feasible. This is not the correct way to do it, because it might happen that the capacity of the bag is very less and no item is getting no item, you cannot pick any item. So suppose over here the items are from weight of 1 to 10, and suppose the capacity of the bag is just 1, and what may happen is you will not have any solution. So suppose all the items have weight of more than 2 or something like that. So this is not the correct way to do it, but just to explain you, so I've taken it like this. Okay, so we will generate an item until so we'll generate a solution until we get a feasible solution. In the later case, when we are talking about simulated annealing, then I have tried to repair, but to make this understand the first problem, I'm taking it this way. Okay, now what I'm doing is I am creating a variable named best solution, and I'm storing this solution because I have only one solution, and that is the solution I know. So I'll say this is the best solution I currently have. And this evaluate function is actually the objective function. It tells me what is the objective function of this problem, or not problem, the objective function which is picked by this current solution. So this evaluate function takes the solution, it takes the item parameters and the capacity of the bag, it calculates the value, and it calculates the weight. What it gives the value if the weight is less than the capacity, less than equals to capacity, or it gives 0. You can give it -1 also. So it will mean, so when this is -1, it means that it is not feasible. If it is giving you the value, then it means it is a feasible solution. So this best value is actually the fitness of this, not fitness, the objective function of this solution. So we have a solution, we know its current objective function, right? So we'll come to these. What are these? So what I'm doing is I'm creating a while loop, and it runs when this improved is true. So to start the loop, we have just taken improved is equals to true, because if the improved is false, this while loop will not run. So the first iteration to run it, we are just saying improved is equals to true. Now before going forward, what we have a current solution, we know its objective function, we need to generate its neighbor. If we are able to generate its neighbor, then we can check each neighbor one by one and check its objective function value, right? So what we'll do is we will, so how will we generate its neighbor? So the neighborhood is taken as flipping one bit. So if I have, so I'll just show you. So suppose this is the initial solution I have. Suppose this is the initial solution I have, right? So this is the solution. So how will we generate neighbors? Flipping this 1 to 0 will create one neighbor. Again, flipping this 0 to 1 will create another neighbor. Again, flipping this 1 to 0 will create another solution. So we are just flipping one bit, and we are saying that is its neighbor, the current solution's neighbor, right? So over here, when we come, then we'll see for each element in this current solution, what we'll do is we will copy the current solution. We'll call it a neighbor. So this is a variable called neighbor. We are just copying the current solution, but we have to change that element. So if the first element I is equals to 0, it will change the first element. So if it is 1, it will become 0. So 1 minus neighbor. So if it is 0, then it will store 1. If this is 1, then it will store 0. So we are just flipping. If it is 1, it will become 0. If it is 0, it will become 1. Instead of this, you can write a if else statement also, right? So I have just made it 1 minus neighbor. You can write if else. So you can say if neighbor I is 1, then neighbor I is equals to 0, else neighbor I is equals to 1. So we are just flipping that element in the current solution, right? Now what I'm doing is I'm evaluating the objective function, the value of that solution. If it is more than the best value, then we'll store it in as a new solution, the new better solution. So if the new neighbor which I have is better than whatever I have currently, so in the initial iteration, the best value is actually the objective function value of the current solution. So if it is more than this, obviously the solution is better. So we will store that solution in best solution. We will again evaluate the objective function of this best neighbor, and we will say we have an improved solution, right? Because we have obtained an improved solution. And when this is true, then it will go back. And by the way, this is running. This will run for n number of iterations. That is, we will create all the neighbors. You see, this for loop will run from 0 to n, right? So it will create all the neighbors of this current solution. It will generate all the neighbors. And when it generates all the neighbors, it moves to the best neighbor. So you see, at each iteration, we are moving to the best solution. And when this for loop is completed, so when we are exhausting the whole neighborhood search, we are storing the new solution. So we are saying current solution, it becomes the new. So the new best solution becomes the current solution. And again, we are going to the while loop. It is checking if we have improved solution or not. And then this while loop is iterating. So what this while loop is doing is the while loop is moving from one neighborhood to the other. This for loop is checking the neighbors in one neighborhood. So this while loop is for different neighborhoods. This for loop is inside a neighborhood. What are the neighbors? When this while loop is completed, then we will terminate and we will say this is the best solution we could find, starting with this random solution, right? So this is how this local search works. Any questions before we move forward? How it is exhausting the neighborhood, how it is moving from the one neighborhood to the other? Any questions? Is the code clear? Just please see once, right? The idea is simple. We will start with one solution. We will exhaust its neighborhood. If we have a better solution, we'll move to that solution and again search its neighborhood. So this is what this code is doing. Is that clear that this code is doing the same thing? Right. Okay. So I see one a thumbs up. So I assume it is clear. So you see, this is a local search where we are exhausting the neighborhood. When this n is large, when the number of neighbors in the neighborhood is very large, then it is time consuming to exhaust the neighborhood. What you can do is whenever you find a good solution, you just move to the solution. So it is known as first improvement. So whenever you have an improvement, you just move to that neighbor. You don't need to search the whole neighborhood. Over here, what I am doing is I am moving to the best neighbor in the neighborhood. I am searching the whole neighborhood. I am finding which is the best neighbor in the neighborhood, and then I am moving to that neighbor, right? Lekin in the other case, when we are talking about first improvement, it is searching the neighborhood, but whenever it finds the first better neighbor, it moves to that neighbor. Okay, so this is random local search. I have named it knapsack. You could have named it as first improvement local search knapsack. I have just labeled as a random. So this name is up to you. So it is totally up to you. You can just change the name. A better name would have been first improvement local search. Okay. So I'll just change it, maybe first improvement local search. So I'll say first improvement local search. Okay, so I've changed the name to first improvement local search. So the code is actually very same. The idea changes over here whenever. So what it is doing is, first of all, uh, till this point it is same, right? We are generating one random solution, we are storing it into the best solution, we are obtaining its objective function value, we are saying improved is equals to 2 to start the loop. Then over here what I am doing is I have this neighbors as a list. So where is this list? So this is actually creating a list from 0 to n, n minus 1. So this neighbor is actually a list. I am randomly shuffling the neighbors. Why I am doing so? You see, if I don't shuffle, I will always start from 1, then 2, then 3, then 4. I'll go to n. To terminate, so to escape this sequence, because I'll in for loop what happens is I always start with 0, then goes to 1, then goes to 2, and so on, right? So to escape this way, I just did is I shuffled these values. Instead of starting with 1 2 3 4 5 6 till n, it is shuffled. Okay, so it is shuffled, and now when I iterate over this shuffled neighbor, I can start with any neighbor. It may be 57 is the first neighbor I am checking, or maybe 58 is the first neighbor I am checking, or it might be the second neighbor I am checking first, or so on, right? To make it random, that is why I have shuffled the neighbors, not to start with always one. So that is why I am shuffling, and then this I is for the index of that neighbor. It can be 27, it can be 39, whatever it is, right? Now I am just doing it one by one. I am storing the current solution as the neighbor, and I am flipping that bit. So if I is suppose 37, I am flipping the 37th bit from 1 to 0. If I is suppose 3, so I am flipping the third bit. I am flipping it from 0 to 1 or 1 to 0. Okay. And then I am evaluating the value of the neighbor. If the neighbor's value is more than the best value currently we have, then I'm storing it into the current solution, and I'm saying best value is this value. And what I'm doing is I am also storing it into the best solution. And then I am breaking. Why I am breaking? Because I know that I have found a solution which is better than the current solution. When I break, then this for loop will terminate. So it will not check the other neighbors in the neighborhood because it has found a good solution. And then it will go to the while loop. So what this while loop is doing, it will move to the next neighborhood. So it was searching the neighborhood of solution. Suppose it was X, it will go to the X plus 1th solution and then search the neighborhood. The only difference is whenever I find a good neighbor, I just break the for loop. I'm saying don't search the entire neighborhood. Just break out of this for loop. You don't need to search the entire neighborhood. And then I am uh, when the while loop is terminated, that is there is no better neighbor in the neighborhood, then we are returning. So you see, when there is no better neighbor in a neighborhood, all the neighbors are being checked, right? All the neighbors are being checked. This for loop will actually randomly, so it will not start with 1, it can start with any number, but it will search all the neighbors if there is no better solution in the neighbor. And in that case, the while loop terminates and it gives two um, outputs, the best solution and the best value. So what I'll do is I'll run the complete code once and I'll show you something. Okay. So in this code, I have local search, exhaustive neighborhood search, local search, first improvement. I have simulated annealing, and I have genetic algorithm. So 4 codes are here. I'll show you the results of all the 4 codes. Okay. So you see, this is the local search. So when I do just local search, we had to just go to 2 neighborhoods, the first neighborhood and the second neighborhood, and total we had to check 40 neighbors. You see, in one neighborhood there will be 20 solutions, right? Because we have 20 elements and a neighbor is created by changing one of the elements. So for 2 neighborhoods, I have to check 40 neighbors, and that is how this number is coming. And this is the best solution it could find in these 2 neighborhoods, and the best value is 452. The capacity was 50, but it used 49 capacity of the bag. One is remaining. The time it took is 0.2973 milliseconds. When I'm do random, this was not random, first improvement. So I'll just change this to first improvement. First improvement, right? So when I'm do first improvement, I also did 2 neighborhood search, but the number of neighbor check was less. I checked only 29 neighbors, and the solution I got is 449. So you see, earlier it was 452, but currently I have 449, right? And the capacity is used to full 50 to 50. But you see, although the objective function value is worse, but the time it takes to run this is less. You see, this is 297 milliseconds, but it only 0.297 milliseconds, but it only took 0.184 milliseconds. Okay, so I have shown you 2 runs, different functions, but I'll show you the other functions as well, the solution it is getting. So this is simulated annealing, right? And this simulated annealing is producing better results. It is giving you a value of 503. So you see, this local search gave you 452, first improvement gave you 449, simulated annealing gave you 503. It had a 150 iteration, 135 iterations, and in total it checked 46 neighbors. I'll tell you what this is. And you see the time it took was more. It took 0.603 milliseconds, right? So what does simulated annealing do? It goes to a neighbor and there is a probability. So if the neighbor is worse, there is a probability of movement to that neighbor. And if the neighbor is better, it will always move. So there is a chance to escape a local optima. So you might be stuck in a local optima in these 2 cases, but there is some probability that you might escape a local optima. So that is why simulated annealing generally performs better. It may not always be the case, but it generally performs better. And this is genetic algorithm. So I'll tell you about genetic algorithm, but let's see the result. You see, this genetic algorithm has the highest objective function value. So it is the best solution it could find, 625. And it used capacity less. It has a capacity of 48. So 50 was the capacity. It used only 48 capacity of the bag. But you see, there is a trade-off. These all took less than 1 millisecond. All of these. So these are very significantly less than so 1/10 of a 1/20th of a millisecond, 1/10 of a millisecond or something like that. But this took around 158 milliseconds. So this is taking a lot of time, genetic algorithm. And this is the graph. You see, I had given it 100 generations. So this is how the objective function value improved generation after generation. So it started from over here somewhere around maybe 506 or 7. That is where it started, and it moved to maybe 595 in 20 generations. And this 525 was achieved in less than 30-35 generations. You see over here it peaked, and it is constant for some number of generations. So yeah, because this is not a single solution search, it has a lot of individuals in the population, and each individual is evolving. So it takes a lot of time. It also takes memory. So genetic algorithm, you have to store the solution of all the individuals. Whereas in this local search simulated annealing, we're just storing that individual neighbor. Okay. So we'll move to simulated annealing, the code of simulated annealing, and then we'll move to the code of genetic algorithm. And mind you, so we are just solving knapsack problem. I want to give you an assignment of running either of the four algorithms. So you can either do local search, or you can do first improvement local search, or you can do simulated annealing, or you can do genetic algorithm for traveling salesman problem. I'll give you some hints for talking about the neighborhoods or maybe mutation, but that will be the assignment for this week. Okay, so you have to run either of the four, only one, any one of the four for traveling salesman problem. Okay. So before I move to simulated annealing and genetic algorithm, any questions? Just a minute, I'll mute silent my phone. Okay, so I'm assuming no questions, right? Okay, so what is the idea of simulated annealing? So you see, in these, suppose in first improvement, so what I'm doing is I'm shuffling the neighbors. So in simulated annealing also I'll shuffle the neighbors. And over here you see, whenever there is an improvement, then only I am moving to that neighbor. Simulated annealing is little bit different. It is quite similar to this, but it is little bit different. So what it does in simulated annealing, so if it is a better neighbor, you just move. So the probability of movement is 1. So whenever you have a better neighbor, you move. But so there will be an else statement in simulated annealing. Else, if the neighbor's value is less than equals to the best value, the probability of movement will be calculated by that function. So whatever that function was, and then there will be some evaluation whether to move to that neighbor or not. So with the probability 1, if we are getting, we will always move to that neighbor. And with suppose probability of something, suppose 60% of the time, then it will check if it should move to that solution or not. That is the slight difference from this code and simulated annealing. Okay. And one more thing. So in simulated annealing, we start with a temperature that is known as initial temperature, and that influences the probability of movement. When the, so I'll show you the expression maybe for maximization problem. Okay, so this is knapsack is a maximization problem, traveling salesman problem is a minimization problem. Okay, so simulated annealing, probability, oh sorry, annealing, I'll just show you the probability. So this is the probability. It is for a minimization problem because there is a minus delta C by T. So this T is actually the temperature. This is what I want to show you. This T is the temperature. So if T is high, the probability of movement is high. If T is low, the probability of movement is low. So over here, what is happening is initially the temperature will be very high. What it means is at the start, you do some random jumps, but when you have done some number of iterations, you should converge, right? So that exploration and exploitation. So in initial iterations, you explore the neighborhood. So the temperature is very high, but there is some cooling rate which decreases the temperature, and the probability of moving to a solution decreases after some iteration. So iteration over iteration. Okay. So first I'll show you the parameters. So I'm starting with 1000 degree centigrade, you can say. And this cooling rate is a multiplier. So at next iteration, 1000 times 0.95, which is 950, and then again 0.95, 0.95, 0.95. Okay, so this is how the temperature will change. I am also giving a maximum iteration limit, so it is 1000 iterations. It will not go to such high iterations, but for your safety you should give some more termination criteria, otherwise you may get stuck in an infinite loop or something like that. For that case only I have given a maximum iteration limit. So if the iteration becomes more than 1000, it will just stop. Okay, whatever the solution, the best solution at that iteration is, will be returned. So these are the three new parameters given to simulated annealing. And also observe, simulated annealing requires more parameters. These are the parameters which were not needed in local search. Okay, so these are the parameters we have to provide. So we'll go to simulated annealing. Again, it is very similar to the other two. So this is the evaluate function, same as before. Over here I have created generate neighbor function. So over here what I am doing is, in the initial one I am just generating a neighborhood, right? Sorry, generating an initial solution randomly, random choice 0 1 from 1 to n, and that I am doing over here in a similar way. So it is very similar. You just check, it is very similar. So what it is doing is, I'll tell you. So this generate neighbor is, it will take, okay, this is generate neighbor. Just a minute. So where is the current solution? Random feasible solution. Okay. So it is, okay, it is generating random feasible solution. Okay. So this generate neighbor, what it is doing is, it is generating a neighbor. So over here, that is being done over here. This is being done in this function. So over here, what it is doing, it is storing the current solution as the neighbor and then flipping one of the bit. So I have made a function over here. What I'm doing is, I'm taking that solution, I'm storing it into the neighbor variable. I'm randomly creating one index. So it can be 1, 2, 3, 4 up to n. It can be any index, and I'm flipping that index. So I'm doing it in a slightly different way. Okay, I'm taking one solution, I'm flipping one random index. It can be any index, it can be from 0 to n, any n minus 1, any index, right? So that is how this generate neighbor works. It takes a solution and generates a neighbor. This random feasible solution, what it does is, it generates a random feasible solution. So initially I was doing it like this. I'm generating a random feasible solution, but I was not, I was running a while loop until I get a feasible solution. So that, I told you, might not be a good way to do it, because you might not have any feasible solution, or the feasible solutions are very less. So this will get stuck in an infinite loop. So to overcome that, I have made a function over here. It says random feasible solution. It takes the item and capacity. First, what it does is, it makes all zero. So it will make all the elements as zero. So nothing is picked. Okay. And since nothing is picked, the current weight is zero. Now what I will do is, I will shuffle the elements, the 0 to n, I will n minus 1, I will shuffle it. Why? Because if I do just for loop, I will always start with 1 and then with 2 and then with 3. Therefore, I'm shuffling it. So this shuffle actually shuffling the indexes. So this range will create index 0, 1, 2 till n minus 1, and it will shuffle. And what it will do is, this for loop will run in this shuffled index. Now, for that index, it will make it 1. So if, so currently the weight is 0, it will see if the item when picked, the weight of that item plus the current weight which I have is less than the capacity or not. If it is less than the capacity, then that item will be picked, right? And we add that capacity to the current weight. Again, for that next index, it will see if the weight of that item included with the already included items, if it is less than the capacity or not. If it is so, then it will pick that item, and then it will add that to the current weight. So this is one way to generate a random solution. There can be multiple ways to generate a random solution. So again, I'll tell you what I'm doing. I am just shuffling the items. So imagine that there is a bag and all the items are put into that bag, and you are just blindfolded and you are picking one item at a time. So if you pick one item And if that item can be fitted in your knapsack, if it doesn't exceed the capacity, then you fill that knapsack. Again, you put your hand in that bag, you pick one item. If you can fit that item in your knapsack, then you put it into that knapsack, or you put it back, something like that. So that is what is happening over here, right? That is how I am generating random solutions. So I will see how many items are there. Then I will create one random solution. I will evaluate its objective function value. I will store this solution as the best solution. I will store this objective function value as the best value. I will make the temperature equal to the initial temperature, and these are just counters, so doesn't bother about it. It says that if the initial temperature is more than 1 or the maximum number of iteration is not exceeded, the while loop will run. What it will do, it will get a neighbor of the current solution. So currently this is the solution I have. It will get the neighbor of that solution, one neighbor. It will evaluate its objective function value. Now, if the objective function value of this neighbor is more than the current value, the acceptance probability is 1. Else, the acceptance probability is calculated like this. So it is that expression. And mind you, this is a maximization problem, so I don't have a negative sign over here. Now, this random.random will generate a random number, and if it is less than the acceptance probability, then we accept that neighbor and we store that as the current solution and current value. And we say, yes, we have moved to a new neighbor. So this count is just storing how many neighbors I have moved to. So initially that count was 0. When I move to a new neighbor, I will just increase 1. So it is just storing how many neighbors we have moved to. And this iteration, it is checking how many neighbors I am checking. So this is actually storing how many neighbors I am moving to. This iteration is actually checking how many neighbors I am checking, right? And if the current value is more than the best value, we will update this best solution and best value. And at last, we have to modify the temperature. So the temperature was 1000 initially. I just multiplied it with the cooling rate, which was 0.95. So the temperature will become 950 in the second iteration. And this iteration will continue, right? And it will just print how many neighbors it has visited and how many number of iterations this while loop took. So these are the two things printed, and then it returns. So if you come back, you will see that we, oh, not this. So we moved to 46 neighbors, but we had to take 135 iterations. Okay. And you see, this is giving you better results. So this simulated annealing, is it clear? The idea, I guess, is clear. Whether the implementation was clear or not. Any doubt? If you could respond, then it will be better. Okay. So I'm assuming it is clear. So you see, we have seen two algorithms, actually three, but yeah, two algorithms for single solution meta heuristic. This genetic algorithm is a population based meta heuristic, right? So for genetic algorithm, you have to have the initial population size. So I am saying the population size has to be 20. Number of generations I have said is 100. So this is my termination criteria. Whenever the 100th generation is reached, terminate. So that is my termination criteria. And I told you there is a mutation rate. Whether to mutate a solution or not is being obtained by this probability. So 10% of the time. So there is a 10% probability that a solution will be mutated, or a child will be mutated for that matter. So what is this? This function is generating an individual. So you see, if you were absent yesterday, not yesterday, the previous class, in the population based meta heuristic, each individual represents a solution. And in a population, for this case, there are 20 individuals. That is, we will have 20 solutions in our at any iteration, and we will try to perform some modifications to these existing individuals, some kind of reproduction, such that there is mixing of solutions such that it moves to the next solution, and in the hope that the next solution is better than the previous solution. So that is how it works. So this function generates a individual. So this generation of individual and this generate random feasible solution is very similar. If you just go back and read both of the functions, it is same function, just different names because the context is different. It takes n, it takes items, it takes capacity, it randomly gets the index. For each index, it checks if the capacity is less than, so the weight of the item plus the current picked items should be less than the capacity, then it is 1 or it is 0. So very, very similar function, same function actually. This function is a repair function. So over here we need a repair function. Why? Because when we do reproduction, so when two parents solution combines, you may create a infeasible solution. For example, in this knapsack problem, you may create a solution which exceeds the capacity of the bag. So I have created a repair function. You can just reject the individual as well. So you can say this individual or this child is not feasible. I'll just reject it. But rejecting a solution is a bad practice. Why? Because you are putting so much effort in creating a child. Why would you want to reject that effort? So you are just rejecting your effort. So it is better to find some repair strategy. It depends upon the problem, by the way. This repair individual is problem dependent. So over here, this repair will work with knapsack problem. It might not work for, it will not work for traveling salesman problem. So it depends upon the problem, what strategy you are using. I have talked about one repair strategy, not repair strategy exactly, one crossover operation in yesterday's class when we were talking about traveling salesman problem. So that if you refer to that, that might be helpful. And when I ask you the question, I'll give you hints of how to do repair and how to do crossover. These things I'll give you hint because those things are not what I want to test you on. Those things I'll give you how to do repair, how to do crossover. Those hints I'll give you. You just have to focus on writing this algorithm, right? So that will be given to you. So over here, this repair strategy, what I'm doing is I'm taking one individual which needs repair, and if it needs repair or not will be checked by this function. It takes the capacity and the items. So it checks if the current weight. So this is how I'm obtaining the current weight. If you don't understand, you can just use your for loop. So this is one line. So Python is actually useful for such codes. You see what I have written over in this one line. If you code in Java or C++ or some other language, you might have to write this in 4 or 5 lines. So Python helps like this. So this is a very compound statement. If you don't understand this statement, it is, don't worry. This is a very, very compound statement. You can just use a for loop. It will take 5 or 6 lines, but it will do the exact same thing. It is iterating. So it is iterating over each of the items and then summing the weight of the item. Right? So it is what it is doing. You can just do what you will do is you iterate over this individual one element at a time. If that element is 1, you add the weight of the item. If that element is 0, you ignore. So you can do that in multiple lines. I have done it in one line. So what it checks, if the weight of the items is less than the capacity, it returns that individual. So there is no need to repair. You just give that individual back. If it needs repair, then what it does is, this is actually one line, by the way. This is complete one line. So I'll just write it in that way maybe. Okay, it goes beyond the space over here. So this is one line. Okay. So this is one line. What it is doing is, I'll just make it as it was for readability purpose. So what it is doing is, it is actually iterating over this list. How it is iterating? You see, I have some number of items picked in this individual. This individual will have some number of items picked. So I'll tell you the concept of this while for loop. You just understand what it is doing. You can do this again in many number of lines. I'm doing it in one line. It is known as Pythonic way of doing it. You can just do it in many number of lines. Exactly the same thing you can do. I'll just give you the idea. So you see, this individual will have some number of items in the bag which is picked and some number of items which is not picked. So whichever item is picked, it is equal to 1, that value is equals to 1. Whichever item is not picked, that value is equals to 0. So what this what this for loop is doing is, it is actually first sorting the items. So whichever item has the maximum weight is being written in one, so kept in. So what I'll do is, I will just do it for you. So I'll just take this out. I will write sorted items item list is equals to this. So this is what sorted item list is. And this for loop is actually running in this sorted item list. Okay. It will be better for you to understand later. So this for loop is running on this list. So what this list is actually is, it is just sorting the items in terms of its weight. So the highest weight item is first, then the second weight item, then the third weight item, and so on and so forth. This is what this list is. And this for loop is iterating over this list. If the current weight is less than the capacity, we break out of this loop and return that individual. Otherwise, we will just make that item as 0. So we'll say this item, you just reject that item because it is exceeding your capacity, you reject that item. Instead of doing so, so over here I am sorting that item in terms of the weight, decreasing of the weight. You can just pick randomly. So you can say, I'll pick one item randomly, I will make it 0 and check if the capacity is exceeded or not. That also you can do. I have picked one way of doing the repair. You can pick other ways of doing the repair as well. Okay. So over here I'm sorting the items in terms of the weight. You can do it randomly. So you can just pick one item, remove that item, again pick one item, remove that item, and so on and so forth. So this is the repair strategy. So you give it an individual, it will return you a feasible individual. This is the function which gives you the fitness. So fitness is same as the objective function value. So it is just getting the total value of the items picked for this individual. This select, you see, we talked about parent selection. So this is parent selection from that entire population. So this is the population. This select is returning two parents. How it is doing? It is doing Role selection. So what is Role wheel selection? I told you there is one wheel and the probabilities. I'll just show you that Role wheel selection. So I'll show you this. So this is how, so that's a pie chart. You can imagine a pie chart. So this is how a Role wheel selection is done. So whichever has the highest fitness will have a higher area in the Role wheel, and you run that, turn that Role wheel, and whichever this arrow points to, that is selected as a parent. And if you have to select two parents, you put two arrows in random locations and you just rotate the wheel, whichever that arrow points to, that will be your two parents, right? So this is what it is doing in this code. This line is actually doing that. It is picking two parents from this population. How it is doing, you see, instead of imagining it as a wheel, what it is doing is, for this population, it is a list actually. It is giving this weight. What is this weight? This is weight is actually equal to the fitness. So each individual in this population has a fitness of whatever it is. So what the objective function value, it is getting as the fitness of that individual. And this random choice is using these weights as the probability measure to select two parents, two individuals, using this as the probabilities. So whatever the fitness is, it will convert it into probability. Higher the fitness, higher will be the probability. And this random choice will pick two parents from this population. And by the way, if you are imagining that how will we know these functions, you can just Google. So and if you are not able to Google, you can use ChatGPT to ask कि मेरे पास एक population है, I have some fitness value, how to pick two parents, right? So if you don't know these, you can use internet to get these functions, because the idea of this lecture is not to make you memorize these functions. As and when you code more and more, you will be able to use more and more functions, right? So but I will tell you that don't use ChatGPT to write the whole code. The main idea is to make you write the algorithm, so that you have to learn. If you are getting stuck in some function कि कैसे करना है parent selection, you can take help of ChatGPT or other GPT tools, right? It will help you pick two parents from a population or something like that. So this is row level selection. Now this is crossover. So it takes two parents and it randomly selects a point. So you see we are doing 1 point crossover. We are randomly picking that point, and from the first parent I am taking one half and the second parent I am taking another half, and I am just storing in child. Now what I am doing is I am passing that child to repair individual because I want to have a feasible individual. Now this repair individual will give me a repair child, and this crossover will return that repair child. Again, I have a mutation function. So you see what are the functions we talked about currently. We can generate individuals for the initial population. After that, you will not use this function. It is only required for the first iteration to generate the first population. This repair individual will be required when we do crossover. Some individuals may become infeasible. So this repair individual will help to make some infeasible solution to become feasible. This is the fitness function. This is parent selection. This is crossover operator. This is the mutation operator. How are we doing it? You see, we take one individual, we take the item and capacity, and we take the mutation rate, right? Now what I'm doing is I have created a list of individuals. So this is just indexes 0, 1, 2, 3, 4, and I'm shuffling those indexes as we have done earlier. And for each of this index, I will generate a random number and I'll check if it is less than the mutation rate or not. If it is less than the mutation rate, then I will mutate that individual. And again, I will do repair strategy because in some mutations that individual might get infeasible. So I don't want to pass an infeasible solution. So I will repair that individual and then return. So these are the helper functions we require for the um, uh, this genetic algorithm. Now we will run the genetic algorithm. Okay, so these are the helper functions. And how do we run genetic algorithm? We start with a population. We pick some parents, whatever the size of the parent is. So over here we will see how many parents I have picked. I don't remember. Half, right? So I'm picking half of them to become parent. Now those create children. We combine the whole population. We pick some of them to become the next generation, and we will see how we are doing it. So n is the size of the population. We are generating these n individuals. We are using this for the graph. So you see I have a graph over here, this graph. If you don't want that graph, so this line is not required. So for the time being, just forget about this line. Okay. So this for loop is for generations. It will run for 100 number of times because we have 100 generations. Initially, the new population is empty. For each of the, so this for loop will run half of the population size. If the population size is 20, it will run 10 number of times. It selects two parents and generates two children. Okay. It selects two parents and generates two children, and it appends the children to the new population. So you see when it is generating this two children, it is doing crossover, and every time I'm doing crossover, you should realize that it is repairing also. So no solution is infeasible. Everything is feasible, right? So everything we have taken care in these functions, everything we have taken care. So this crossover is giving me a feasible child. This also giving me a feasible child. So for these two child, I will pass to mutate function. So this is the mutate function for child 1. This is the mutate function for child 2. And we are adding these two mutated children to the new population. Okay. So we are getting a new population. So this for loop runs when we get a new population. Now what I'm doing is I'm combining both of the population. So this is the combined population. Okay. And then we are picking 80 best individuals. So what this sorted population is doing is it is sorting the individuals in the combined population in the decreasing order of fitness, and then it is taking 80% of the individuals initial. So whatever the population size is, suppose the population size is 20, so it is taking the best 16 of them from the combined population. It is taking the best 16, the best 16. So this is what it is doing. For your simplicity, you can just take the best of best 20. So for here, I'm just doing best 16, and the four number of, that is the 20% of the rest, are being randomly picked from this minus this. So what I'm doing is combined population minus the selected population, whatever is the remaining from the remaining individuals, I'm randomly picking the other 20%. So that is what this is doing. So these are just improving the genetic algorithm, right? These are just improvements. You might not do it because it is not necessary. You have to realize that I want you to learn the algorithm. These are improvements in the algorithm. Okay. So we are just saying the new population is the selected population 80%, and then the remaining population. So we are adding these two populations and storing it into population. And then from this population, so these things are required for the graph. So for each generation, I am picking the best individual and the best fitness, because I need it for the graph. For each iteration, I want what is the fitness. That is why I can plot the graph. So these two lines are just for plotting. Okay, so you can ignore it for now. When I have the new population, it will go to the next generation and it will do it again. Now these lines are for the graph. You can just ignore. At last, when this for loop terminates, we have exhausted all the generations. Then it picks the best individual in the last population and then returns the best individual and its fitness. Okay, it is returning, and that is how we are getting this graph. You see, this is the graph which is being plotted. This is the solution, and this is the value of this solution, and these are the items that are picked, and this is the total weight, 48 out of 50. The time it is taking is 158. You can decrease it. If you are saying that I will not go for 100 generations, I will go for 40 generations, that can also be the case. But always remember, these lines may change generation after generation. Okay, so what I'll do is I have these numbers randomly generated. So I will say I will make this as constant for the time being. So I'll just say item is equals to this, and I will remove this random generation. So this data will be constant for now. Okay, this data is constant, capacity is also constant. Now you see, this local search gave me 452, this local search gave me 449, this gave me 503, and this gave me 625. I will rerun it. You see, it will change. So you see, this local search gave me 458, this gave me 312. So this is very worse than before. And this gave me 615, and this gave me 625. And you see, it is actually converging at around 30-35 generations. And you observe, we again obtained 625. I will run again, it may be we again obtain 625. Again you see 625. So we can have a hopeful guess that this is the best solution it can have, 625, but we are not sure. Again, I will go back to that idea that this 625, this solution may be the best solution, maybe, but we are not sure that this is the best solution. Okay, so there lies the catch. You can run it many number of iterations, and maybe this is the best, because we are getting it in every iteration. You see, we obtained this as around 80 iterations, 80 generations, but we are not sure. Maybe if you go for 10,000 iterations, it may improve. We don't know. So this is why these algorithms are known as approximate algorithms. Any questions? Any questions? Okay. Okay, so what we'll do is we'll take 5 minutes break, and then we will talk about constraint satisfaction. That is the last part of optimization, and from next class we will move to machine learning. Okay, so we can meet at 7:05. I'll stop sharing and then I'll start sharing my iPad. Yeah. All right. So today is the last portion of this optimization, which is constraint satisfaction problem. And there is very good likelihood that you have already encountered these kind of problems. So we will go through it and then you will realize that these are very commonly encountered problems. So for example, if you have done Sudoku, so what is a Sudoku? See, Sudoku is a 9 by 9 grid. Okay, Sudoku is a 9 by 9 grid and it has some constraints. So each grid can be filled in with a number from 0 to 9, right? Each grid can be filled by a number from 0 to 9 and there are rules how you can fill this grid. Okay, there are certain rules how you can fill this grid. So if you fill a number over here, suppose it is 9, then there cannot be any other 9 in this row. There cannot be any other 9 in this column, sorry, column and row, and there cannot be any other 9 in this 3 by 3 square. Okay, so these are the constraints. You see, these kind of problems are known as constraint satisfaction problem. You don't have an objective, right? You're not trying to minimize something, but you're trying, this is search problem, you're trying to find a state. So when all are filled, it is a state. You're trying to obtain that state, and you start with some elements fixed or some or all elements empty, but you are going from one state to the other. When you write suppose 3 over here, you move from one state to the other and so on and so forth, and you try to reach the goal state. Okay, so this is a search problem and you don't have an objective, but there are constraints. That is why these problems are known as constraint satisfaction problems, and we'll see an approach or an algorithm how to solve this problem. Okay, so you see, since we have talked about this state states and goals, so this can be used, the algorithms which we saw when we were talking about state space search can be used over here. So you can use depth first search, you can use breadth first search, and so on and so forth. But we'll see why those algorithms are not very good, and not efficient to solve these kind of problems. There are better algorithms to solve these kind of problems. Okay, so first we'll have an introduction to this constraint satisfaction problem. In short, it is known as CSP. So CSP involves assigning values to variables while satisfying specific constraints. So where are these variables? What are the values? Okay, so we'll see that first. So over here we have 9 cross 9, 81 cells, and we'll say each cell is a variable. So suppose this is a cell, it will be xij. We will write it as xij, and this specific cell is actually x29, right? So each cell is a variable over here, xi comma j. Each cell is a variable and it has a domain. What is the domain of this variable? It is actually any number it can take, 0, 1, 2, 3, 4 till 9, right? So this is what it says. Constraint satisfaction Constraint satisfaction problem involves assigning values to variables. Over here you see each cell is a variable and we are trying to assign a value to that variable such that we have to satisfy the constraints. So when you are assigning a value to this variable, which is this variable, this is x11. When you are trying to assign a value to this variable, you have to satisfy the constraint. What are the constraints? No no variables in a row can have the same value, no variables in the column can have the same value, no variables in this 3 by 3 grid can have the same value. These are the constraints for this constraint satisfaction problem. Okay, common example, graph coloring problem. So this is a very famous problem around, so I don't remember the year, maybe 1880s, or I don't remember the year exactly. So what was the idea? So there were graphs, right? So in India, there are states And the idea is, suppose this is a state, this is another 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 state. So these are the different states in a country. So the question is, you have to color this graph. You have to color this graph, right? You have to color this graph such that no two adjacent state have the same color. Okay, so that is the criteria. And another is over here, another is you use the minimum colors. So this is an objective, by the way. Earlier I mentioned that there is no objective, but you can have objective in constraint satisfaction. The idea is, for constraint satisfaction, you have variables and you have trying to assign values such that constraints are met. So for this problem, there is a objective function. What is the constraint, by the way? Adjacent states cannot have the same color. So in that case, you will say, if there are n states, I will assign n colors. So over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 states, assign 10 colors. But that is not a good thing to do, right? You cannot say just assign 10 colors. You can change this problem a little bit. You can say each state has a domain of 3 colors. So suppose red, blue, and green, or red, blue, or something. RGB, right? R, G, and B, yeah, red, blue, and green. Now you tell me, can you satisfy the constraint while filling all the colors or not? So this is a constraint satisfaction problem with no objective function, right? I'm saying I am giving you 3 colors. Now tell me, can you fill this graph with these 3 colors only, such that no two adjacent state have the same color? Again, I can give you another question where I don't have 3 colors, I give you 4 colors. So red, blue, green, and black, right? Now I can ask you again, can you fill this graph with these 4 colors without with satisfying the constraints? So this is the same problem, but I'm breaking it. I'm saying I'll give you 2 colors, I'll give you 3 colors, I'll give you 4 colors, I'll give you 5 colors. Instead of that problem, I'm saying minimize the number of colors. Okay. So all these problems combined, I'm making one more problem, satisfy the constraint such that the number of colors used is minimized. Both similar problem in convention, but one has a objective function, other not. So we will first work with this problem where I'm giving you the domain of that variable and I'm saying, can you satisfy the constraints and color the graph using only these 3 colors? So you have variables, you have the domain, you have, yes.
No.
Okay. So there are variables. So how will we how will we have variables for this? So what I will do is I will convert this to a graph. What I will do is, for each of these states, I will make a node. So this is for, so I'll label this maybe. So what I'll do is I will say, I'll take another color, maybe, okay, black, I'll use black. So this is A, this is B, C, D, E, F, G, H, I, J. Now you see, you can make this as nodes: A, B, I, J, C, D, E, F, G, and H. And you can connect this if they are adjacent. So A is adjacent to B, you connect this. A is adjacent to J, you can connect this. Similarly, AI is connected, BC is connected, CJ is connected, BJ is also connected. Over here, I am saying it is connected, okay? And so on and so forth. You can make this graph, right? And now what you can do is, you can say these nodes are the variables. So over here, A is a variable, B is a variable, C is a variable. And the domain of A is these 3 colors: red, green, and blue, RGB, the 3 colors. For B also, there are 3 colors: red, green, and blue. For all the variables, there are 3 colors. What are the constraints? Adjacent node must not share the same color. Okay, so this is the complete definition of a constraint satisfaction constraint satisfaction problem. Types of constraint satisfaction problem, there can be multiple types. First is the hard constraint, where I am saying must satisfy that constraint. So over here, when I am saying adjacent nodes must not share the same color, then this is a hard constraint. You cannot violate this constraint. There is something known as soft constraint. So it is actually a preference. So like I can say minimize the number of colors used. So it is preference. Soft constraints. Unary constraint. So you see when I am talking about unary constraint, it affects a single variable. So for example, so by the way, I did not give you context of why this problem was thought out. So when the people were making maps, they wanted to use colors to distinguish between states. And because at that time printing was expensive, they wanted to use less number of colors to print that map. And that is why this problem came into picture. Okay. And this has real applications. I have taken some applications which are very real and can be modeled as graph coloring problem. So this is not just trivial problem right now. Okay, so unary constraints. What is unary constraints? For each node, it says that it has some constraint for each variable. So for this graph coloring problem, you can think that each state has a preference. So state A says, I don't like green. I only want red and blue. So what is it? So A cannot be equals to green. So this is a preference of that state. It can say that I don't like green. I don't want to label my state as green. So this is a unary constraint. It only depends on one variable. It is dependent on one, that is known as unary. One. Okay, unary means one. Unary constraint affects a single variable. When I say binary constraint, it is related to two variables. So over here, this constraint, adjacent node must not be the same color. So over here we can write A not equals to B. You see A and B are adjacent, and when I'm saying A not equals to B, it implies that A's color cannot be equal to B's color. So these kind of constraints are binary constraints. Okay. Again, when I'm saying A's domain is red, green, and blue, this is also a unary constraint. I'm saying red can only have red, green, and blue. This also is a unary constraint because it is only affecting one variable, right? Examples: A cannot be red, A and B not equal is a binary constraint example. Now, these are some techniques of solving these, not solving this problem, which aids in solving this problem. One is known as node consistency. So a variable is node consistent if all the values in its domain satisfy the unary constraint. You see, I have a graph, so I'll just draw any graph. A, B, C, D, E, and F, and I'll connect some of these graphs. Okay. Now, when each of these node satisfy the unary constraint, then I'll say it is node consistent. So each node is consistent. For example, B says that I will. So you see each node has a domain, right? Each node has a node domain. And suppose B is saying don't want green. It doesn't want green. So in the domain you have to, so it has red, blue, and green. So from the domain of B, you have to remove green, because that is a unary constraint. B not equals to green. When you do so, when you remove the unary constraint from the domain of B, then only you can say that node B is consistent. It is node B is consistent. And when you do so for the whole graph, then you can say the graph is node consistent. Okay. So you are just trying to satisfy the unary constraint for the whole graph. When you do so, then you can say the whole graph is node consistent. And for a variable, you can say that for that variable it is node consistent. Okay. So a variable is a node consistent if all the values in its domain satisfy the unary constraint. For example, a variable A has this domain and constraint is A not equals to green. The revised domain should be green and blue. Okay. Achieving node consistency simplifies the constraint satisfaction problem and reduces search space. So if you go back in this problem, Sudoku problem, if you remember, there are some already defined values, right? So there can be 7, there can be 8, 2, 3, and so on. So these are given to you when you have faced a Sudoku problem. These are given to you. Now suppose you are filling this. Now suppose you are filling this variable. So you see this variable has a domain of 0 to 9, right? and suppose there are some more numbers 1 and 2. Now you are trying to make this as node consistent. So currently you are having 0 to 9, but you see this variable cannot have some more values. You see it cannot have 9, it cannot have 3, it cannot have 8, it cannot have 1, it cannot have 2. Therefore the domain of this variable changes. These values will be removed and the domain will be restricted. This is how you solve Sudoku like this. You say that okay, this value cannot be 3, 9, 8, 1 and 2. What values can it have? So you are actually doing node consistency when you are solving a Sudoku. I hope you have solved a Sudoku in some time or the other. Okay. So this is node consistency. Any questions? Okay. Another is arc consistency. When we're talking about arc, so node consistency is related to a particular node. Arc consistency is related to two nodes at a time. Okay, that arc. So when I say A and B is not equal, and for this example you see A is red and green and B is green, so you have done the node consistency and these are the domains of these two variables, and you are trying to do arc consistency. So when you do arc consistency, you see B has green, therefore A cannot be green, so you can just strike green from here, and then you can see A has a domain of only, so that variable is only red, so you can just fix it. Fixing is not the point for arc consistency. The point is you have to remove. So suppose there are more values. A was suppose red, green, blue, black, and so on, and B was suppose red and green. So over here making node consistency is not easy, because you see B can either be red or green, so you cannot just remove red or green. Once this has only one value, then you can easily remove the value from here. So arc consistency you have to check very thoroughly, and then only you can do arc consistency. We will see one algorithm which is known as revise, and by the way these algorithms I have taken from Harvard's lecture. I have given the resources over here. Okay. So what does this function do? It is actually a function which takes the graph and the two nodes x and y. For each x, so over here it will take A and B. What it will do is for this A, it will see what are the values it has. So it has red and green. Okay, for this example it has red and green. Now for y, if it satisfies the constraint, if no y satisfies the constraint, then delete that. So over here suppose we will start with x, then it is better. Okay, so I'll just reiterate the problem. So we will say x is B, and we'll see what is the domain. So it has only green, so we will have x for green. Okay, GREEN. Now what I will do is, if no y belongs to this domain satisfies the constraint between x and y, so you see A has a domain of red and green. This satisfies green, but this doesn't satisfy green. So this will not be true, and then we delete that from x. So currently we cannot delete anything from B, but if x is A, so A has green and A has red, right? This you can do, this you can delete. So what you do, you select, this loop will first iterate over green and red. So when it iterates over green, it will check if no y belongs to this. So y belongs to B has green, so this will become green, satisfies the constraint of x and y, you delete it. So you see, if you select green for A, so suppose you have this for loop has green, and since it has green, you see there is no value in B which satisfies A for green. So if A is green, there is no value in the domain of B which can satisfy A value as green. Therefore you have to delete green for A. So that is how this algorithm is working. I will reiterate. So in A, it will take one value at a time. So suppose it took green. So when it took green, it saw that B doesn't have any other value which will satisfy A as green. Therefore you have to delete green for A. Now when A was taken as red, When A was taken as red, it will see that there is one value in B which can satisfy A as red, therefore it will not delete red from A. That is what this function is doing. It is very simple, it is just doing arc consistency. Okay, it is just doing arc consistency. Any questions? Okay, so it is just modifying the domain of X. So X was A and we were deleting green, so it is modifying the domain of X. Okay, and it returns true. So if it changes A, it returns true. If it not changes A, then it returns false. This is an algorithm, AC3 algorithm, which which does arc consistency for the whole graph. So this revise is actually doing for one pair of one node. Actually for X it is doing, only for X it is doing. This AC3 algorithm, it is doing for the whole graph. So what it will do is it will call revise iteratively. It will pass one pair, it will call revise, and then again it will pass one pair, it will call revise, and so on and so forth. That is the idea. Revise is actually doing the arc consistency. AC3 algorithm is systematically calling revise one at a time. Pass this arc, then again pass this arc, and then again pass this arc, and so on and so forth. This is how AC3 algorithm will work. Okay. So what it will do is start with all the arcs in the queue. So for this graph, it will make a queue. So this is arc 1, this is arc 2, arc 3. So it will take it in a queue. So first arc will be AB, second arc will be AD, then AF, and so on. And this queue, it will dequeue. So one it will take out and then it will pass to revise. For each arc in this queue, it will pass that to revise function. If there is some changes in the domain of X, what you do is, since you are changing the domain of X, it might change. So what I'll take one example, then it is better. I have an example from this lecture only, so I'll take that example only. Just a minute. So this Harvard lecture has a very good example. Okay, I have that example over here as well. So this example is, it says that, I'll take one example, then this algorithms will be clear. So it says that there is students, and these students, there are 4 students: student 1, student 2, student 3, and student 4. This students has some subjects taken. So A has A, B, and C. B has D, B, and E. And student 3 has C, E, and F. And student 4 has E, F, and G. Okay, these are the subjects. So these are subjects A, B, C, D. These are the subjects and these are the students. And what it is doing is, it is saying you have to schedule exams such that these students doesn't have exam on the same day. So what are the days? You have 3 days: Monday, Tuesday, and Wednesday. So there are 3 days. And TUES, just okay. So these are the 3 days you can have exams, but you cannot have exams of, so one student cannot have exam on the same day. And since there are, so suppose you see, you put A and B on the same day, that cannot happen. That student 1 will have 2 exams on the same day. So you are scheduling such that no students have exam on the same day. Okay, so what are the nodes? You see, these exams will become the nodes. So you will have A, B, C, D, E, F, and G. And the arcs will be, for these students, A and B is connected. Okay, B and C is connected, and A and C is also connected. So what it means, A and B cannot have the same value. So what are the domains of each of these nodes? It will be Monday, Tuesday, and Wednesday. Similarly, this will be Monday, Tuesday, and Wednesday. So you cannot have same value for these 3: Monday, Tuesday, and Wednesday. So you cannot have same value, because if it has same, then student 1 has to give 2 exams on the same day. Again, student 2 has BD, DE, and EB. Okay. And similarly, student 3 has CE, CF, and EF, and student 4 has EF, FG and EG. Okay, so this is the complete graph, and each has three values in the domain: Monday, Tuesday, and Wednesday. Monday, Tuesday, and Wednesday. Monday, Tuesday, and Wednesday. Monday, Tuesday, and Wednesday. Okay. Now what you do is, you see, you check for arc consistency. First you check for node consistency. Okay. First we'll check for node consistency. You see, there's nothing you can do right now. Neither you can do node consistency because A can take any three values, B can take any three values, C can take any three values. It's like Sudoku. We will just do whatever we do in Sudoku over here. You cannot do anything for arc consistency as well because nothing has one value. If you have one value, then only you can terminate, remove the other variables domain. So what you have to do is you have to fix one value and move to the other. So what we'll do is we will fix A to Monday. And this we are doing backtracking algorithm. First we will fix a value, we will go down the tree, and if we see that it is not feasible, we'll move back. This is how backtracking works. If you remember in DFS also, we are at a node, we are fixing the value of A to be Monday, and then we will go down. So we will fix B, fix D, fix E, and if we see that this is not feasible, we will come back and see कहाँ से problem शुरू हुआ था. And in Sudoku also we do like this. In Sudoku grid, sorry, in Sudoku grid, we fix one value. Suppose we are fixing 1 over here. We fill more values, and if we come to one point where we cannot move forward, then we see कि कहाँ पे problem शुरू हुआ था. That is known as a backtracking algorithm. Okay, so over here we'll start with Monday. So if we fix Monday, let's move to B. So if this is Monday, B cannot be Monday, let's make it Tuesday. Okay, when this is Tuesday, then D, it can be Monday, it can be Wednesday. So let's fix for Monday right now. For E, you see this is Tuesday, so it cannot be Tuesday, it cannot be Monday, so E will be Wednesday. Now for C, you see, it cannot be Monday because A is connected to C. It cannot be Wednesday because C is connected to E. It cannot be Tuesday as well because C is connected to B. And you see here is a problem. You have get stuck in a problem. Now you have to backtrack because you cannot fix anything for C. You have to backtrack. So let's backtrack. You see, we have backtracked over here. You cannot do anything for E because you cannot have Monday for E, you cannot have Tuesday for E, you have to have Wednesday for E. Therefore you again backtrack. चलो थोड़ा सा और पीछे चलते हैं. Okay, now for D, you see we selected Monday and Tuesday was not possible because B was Tuesday. We could have selected W. So what we'll do is we will remove Monday and we will select Wednesday. Now when we have fixed Wednesday for D, we can go to E. Now you see it cannot be Wednesday, it cannot be Tuesday, E will be Monday. Now when E is Monday, you see C cannot be Monday because two are Monday and B is Tuesday, so it cannot be Tuesday. We have come to Wednesday. Now this is Wednesday. For F, you cannot have Wednesday because C is connected. You cannot have Monday because E is connected, so this is Tuesday. And these two are Tuesday and Monday, so W will come over here. And then we have solved the problem. So this is known as backtracking search. Now you see, during this backtracking search, we never used node consistency and arc consistency. We could have used it. In Sudoku, when you solve a Sudoku, you actually perform node consistency and arc consistency. Remember, when we are solving a Sudoku and we are writing, suppose over here 8, we are checking for arc consistency. We check कि this row में 8 है कि नहीं है, right? And when we put 8, we know that the domains of the other variables are getting reduced. So when we are doing node consistency, when we are putting 8, we are removing 8 from the domain of all the variables over here and all the variables over here and all the other variables in this cell. And we are also doing our consistency. When we are putting 8 over here, we are seeing कि रो में कोई 8 है कि नहीं, डोमेन में कोई 8 है कि नहीं, and जब 8 हम put कर दिए हैं, when we have put 8, then others cannot also have 8. So those are arc consistency and node consistency. We perform that. So we can add that idea in backtracking search and improve the efficiency of backtracking search. And we do that arc consistency using this AC3 algorithm. This algorithm, AC3 algorithm. Okay, so I'll just again come back to AC3 algorithm and then we will move to backtracking search. We have seen backtracking search. So what we do, we start with all the arcs connect in the queue. So we say all arcs are in the queue. For each arc, we move to revise function and we see we take that back. So now suppose I'll take one example. Okay, I don't have an example now. So I'll just think about some example. So suppose, okay, so suppose for this graph, I'll just remove these uh, lines and we'll take one example. Okay. Okay, so you see we have fixed Monday for A. When we have fixed Monday for A, we can do our consistency. So this is how we'll do our consistency for the whole graph. We will move to each of the nodes first. You see, for B, B cannot be Monday. C also cannot be Monday. So we are doing node consistency before putting B any value. Before putting B any value, we are doing our consistency. Again, when I put Tuesday for B, we will again do our consistency. We will just remove T from over here. We will remove T from over here. We can remove T from over here. Now, when we have done our consistency, we can do now node consistency. Over here you see C will only have W and it only has W. So we will do node consistency and we'll put W over here. Now when we have put W over here, we can do our consistency because this cannot be W, this cannot be W, and B also cannot be W. So you see we are sure that B will be T for this case right now. So in doing backtracking
Shubham,
also, yes, yes.
Shubham, E cannot also be T. You
So we
E
will just
B.
follow the steps again. Okay, you just stop me when you see some issue.
You,
So we fixed A as Monday. Now, before doing the backtracking search, we will do the arc consistency and node consistency. Okay, so we have fixed Monday for A, we will do the arc consistency. First, we'll do the node consistency. We don't see anything we can do for node consistency. Then we'll do arc consistency. So B cannot be Monday, C cannot be Monday. Now we can fix B to T or W, either would work. That is again backtracking. So if you select T and you face some issue, you come back, you change B to W. Okay. So we select B as T. So this is a this is we are doing backtracking. Now when we have fixed T, then we will again do our consistency and node consistency. We cannot do anything for node consistency because nothing has one value in the domain. We can do our consistency. So we remove T from here, and T from here as well, right? Then we will do again backtracking. So इसका select हो चुका है. Now we can select. So node consistency we have not done. So node consistency for C we can do. C को W fix कर दिए. जैसे ही W fix किए we can do our consistency. So you see when we have fixed W, this is removed and this is removed and this is removed. अब कुछ बाकी नहीं है. There is node consistency. M को fix कर सकते E में. When we fix M over here, we can again do our consistency. इससे हट गया M, इससे हट गया M, इससे हट गया M. Now again we can do node consistency. We can fix T over here, we can fix W over here. जब इसको T fix किए, इससे T हट गया, यहाँ पे W आ गया. You see, only 2 steps of backtracking search and node consistency and arc consistency से we have a solution. We did not do backtracking at all. पहले का केस में we were doing backtracking. Over here we just did 2 steps of backtracking and everything else was node consistency and arc consistency, right? फिर से फिर से ये steps बताएं क्या?
so, shall I conclude that with the help of R track node consistency, R consistency, we need not have to use backtracking.
No, we improved the backtracking algorithm. We were using backtracking algorithm, but we
No,
improved
I haven't used backtracking.
So suppose when we had selected this M and we were doing node consistency and ये consistency, we came to a point where we are not able to do any assignment to a node. मतलब सब cut हो गया. Then we will come back and change M to T, right?
So no, correct. I got in a trivial solution. There could have been node, for example, say have to have examination. Then we go for a backtracking. But
आवाज आपका कट रहा है. I'm not
going
able to hear you
the
clear.
backtracking, no, a in that help of node and situation, there would not be a examination have, then we would have backtracked the entire.
हाँ, yes. जहाँ
Of
से
course,
शुरू किए थे back track करना पड़ेगा.
we would backtrack with the help of.
आपका आवाज कट रहा है. I'm not able to hear you clearly.
Yeah, are you able to hear me?
हाँ, मतलब now it is clear. बोलिए.
I have a poor connection, network connection, but I'll try myself. Yes. So yeah, absolutely right. We can improve backtracking algorithm, backtracking with the help of arc and node consistency. Correct.
Right.
Over.
Okay. Okay. So we saw that we are using backtracking algorithm, but we are improving it using arc consistency and node consistency. Okay. So this AC3 algorithm is a way to do arc consistency for the whole graph. How it is doing? You see, when we were doing arc consistency, एक को fix कर दे रहे थे, तो then we can again do node consistent, again node consistency, again arc consistency. So back and forth हो रहा है. Suppose we are fixing a value for C, we can again change its neighbors. So C का neighbor E है, C का neighbor B है, C का neighbor A है. So when we are doing something change, some change to C, we have to make check कि there are can we make more changes to its neighbor. ये idea clear होना चाहिए. When we do some change to one of the nodes, we have to check कि उसका neighbors में कुछ change कर पा रहे हैं कि नहीं. For example, when we fixed W for C, we could remove W from here, we could remove W from here as well. So कोई भी नोड में चेंज कर रहे हैं, उसका नेबर को मुझे चेक करना है, and that is being done over here. Okay. With that idea, we'll be able to understand this algorithm very nicely. So we start with all the arcs in the queue. We take one of the arc, कोई भी एक arc queue से लिए, कोई भी हो सकता है, it's not arranged anyway. We pass it to revise function, and you see this revise function returns true if it makes a change, and it returns false if it doesn't make a change. Okay, it returns false. So if there was a change, if change was made to x's domain, check the arcs involved to s involving x. मतलब अगर आप c में change किए हैं, you check the arc consistency for those, for A, for B, for E. That is why this line is required. Check arcs involving X. Repeat until no change or an empty domain is detected. Empty domain का मतलब कि कोई some variable doesn't have any domain. So we have to backtrack. Okay. So this is how AC3 algorithm works. Simplifies the CSP by making it arc consistent. Okay. Yeah. Backtracking search. So ये algorithm we have discussed. Recursive algorithm for solving CSP. Assign a color to one node. कोई भी assign करिए. Check the assignment satisfies the constraint. If consistent, move to the next node. If not, backtrack and try another color. So this is the idea of this algorithm. An example we have seen. Now ये backtracking में I have incorporated the consistency, R consistency and node consistency. We can further improve this algorithm. Okay. Again, I'll tell you. This backtracking algorithm may I have incorporated the R consistency and node consistency. We can further improve this algorithm. How? By doing inferences and using some heuristics. So I have example from the same lecture. I'll give you some examples. Okay, so first is inference. So we did this actually, we did this also. So enforce arc consistency at every node. So this is done, inference is done. Okay, so whenever we are whenever we are fixing a node, we are doing arc consistency and node consistency. We'll talk about this heuristic, but that is known as minimum value, minimum remaining value. So you see, whenever we are fixing over here A, suppose we are fixing A, then we were selecting कि चलो B में हम T करते हैं. We could also selected C. We could also select M, D, E, F, G. कुछ भी select कर सकते थे. Why B? So this heuristic tells me to select that node which has the smallest domain. मतलब इतना सारा नोड्स है, एक को फिक्स करने के बाद यू सिलेक्ट दैट नोड विच हैज द स्मॉलेस्ट डोमेन. सो एक एग्जांपल यहाँ पे दिया हुआ है. आई टेक दैट सेम एग्जांपल. So for example, I'll draw the graph first. So the graph is same. And suppose A is fixed M, B is fixed T, C has one value in the domain, D has two value in the domain, M and W, and E has three value. This also has three value, M, T and W. This also has three value. Okay. Now, according to this heuristic, you select that node which has the least number of value in the domain. So first you see C के पास सिर्फ एक ही है, W. So you just select that and put W. You perform node consistency. So ये W हट गया, ये W हट गया. Now you see again you have a node with three values in the domain, three nodes with two value in the domain. So you select a node with two value in the domain. अब ये तीनों में से कौन सा select करना है? That is another question. Before that, यहाँ पे three value है, यहाँ पे two value है. So you shouldn't select a node with more number of domains. You select the node with the minimum number of values in the domain. तो आप इसको में से कोई एक select करिए. The next heuristic is degree heuristic. It tells me choose that node involved in the most constraint. मतलब you choose that node जो ज्यादा वेरिएबल को अफेक्ट करेगा. So over here you see when you select D, it only affects this and this. If you select F, it affects only 1, 2 and 3. But if you select E, it affects 1, 2, 3, 4, 5. So आप ये तीनों में से select E, because if you fix that value, then you are eliminating more values in the other nodes. Therefore, select the node with the highest degree. Okay, it is clear, I guess. Okay. Okay. The last heuristic is, these are heuristic by the way. It is not guaranteed to improve the algorithm, but these are heuristics. The last is least constraining value. You see, when we are selecting a node कि कौन सा node का values put करना है, we are selecting with the least number of values in the domain. Okay, so 3 का जगह में we selected someone with 2. But this heuristic says सिलेक्ट दैट वैल्यू. अब देखिए पहला वाला में था कि सिलेक्टिंग अ नोड, कौन सा नोड सिलेक्ट करना है. ये दोनों कंसर्न्ड इज सिलेक्टिंग अ नोड. दिस इज कंसर्न्ड इज आफ्टर यू हैव सिलेक्टेड अ नोड, विच वैल्यू टू पिक. क्योंकि सपोज वी हैव सिलेक्टेड ई, इसके बाद वी हैव सिलेक्टेड ई. नाउ देयर आर टू वैल्यूज, एम है, टी है. कौन सा वैल्यू सिलेक्ट करें, एम को सिलेक्ट करें कि टी को सिलेक्ट करें. सो दिस tells me least constraining values. You select that value, assign that color that constraints other constraint the least. आप वो वैल्यू सिलेक्ट करिए जो अदर नोड्स को सबसे कम कंस्ट्रेंट करेगा. समथिंग लाइक दैट. मतलब यहाँ पे सिंस दिस इज टी, तो ये टी खत्म हो जाएगा, यहाँ पे एम आ जाएगा. बट इट मीन्स कि मान लीजिए कि ये यहाँ पे टी नहीं सिलेक्ट कर पाते, so you have to select that node, that value, क्योंकि what is the aim is to obtain a solution. So you select that solution which is affecting the other least. तो यहाँ पे इस केस में क्या हो रहा है कि यहाँ पे समझ लीजिए कि m और t दो है. Now you see we select that node. If you select t, तो यहाँ पे कंस्ट्रेंट इसका फिक्स हो जाएगा, यहाँ पे फिक्स नहीं कर पाएंगे. इफ यू सिलेक्ट टी, यहाँ पे एक नोड में आप टी कैंसिल कर सकते हैं. यहाँ पे टी अगर सिलेक्ट करिएगा तो इसका भी आप कैंसिल कर सकते हैं, राइट. अगेन अगर एम करिएगा तो यू कैन कैंसिल दिस, यू कैन कैंसिल दिस, यू कैन कैंसिल दिस. सो टी सिलेक्ट करने पे आप 2 कैंसिल कर पा रहे हैं, एम सिलेक्ट करने पे आप 3 कैंसिल कर पा रहे हैं. तो सिलेक्ट दैट जिससे कम कैंसिल हो रहा है. व्हाई? बिकॉज द एम इज टू ऑब्टेन अ सोल्यूशन. अगर आप ज्यादा कैंसिल कर दीजिएगा then you might reach to a point जहाँ पे you obtain no solution. So you try to select that value that cancels less in the other variables domain. Okay, because you want to get a solution, you want to select such value that gives potential values to other nodes also, because I want a solution. I just don't want to reject, not reject, I just don't want to eliminate the potential values or other variables take. So this is the heuristic which says select that value for a node select करने के बाद select that value for a node which restricts other variables less. Okay, so this is the idea of improving the backtracking search more. Am I clear? Am I clear? Okay, so I am assuming I'm clear. So some examples of graph coloring problem. So yeah, that is the same example. So I have modeled this graph coloring problem as CSP, which we have talked about. Variables hai, domains hai, constraints hai, and so on and so forth. Applications of graph coloring problem. So you see, for map coloring, we have already seen कि map में color करने के लिए scheduling में it helps. So I'll give you one example of scheduling. So suppose there is an agency which provides taxi, okay, and it has some orders, and these are on time. So this is time axis. So इस time से इस time पर एक order है. So these are some times, maybe 5, 6, 7, some time, right? इस टाइम से इस टाइम एक ऑर्डर है, इस टाइम से इस टाइम एक ऑर्डर है, इस टाइम से इस टाइम एक ऑर्डर है, एंड सो ऑन. ओके, these are the orders it has. Okay, now what you can do is the question is what is the minimum number of taxis this agency required? Suppose he is hiring taxis on the go. So what is the minimum number of taxis he required for this number of orders? So you can model this problem as graph coloring problem. How? So you make these orders as variables. So this is variable A, this is variable B, C, D, E, F, G, H, and I. Okay. Now you see, if you are using a taxi for A, then you cannot use the same taxi for B or C. You can use the same taxi for D, but you cannot use it for, if you use that taxi for A, you cannot use that taxi for B and C. So you make that graph. How you can make that graph? You see, you put A, B, and C, and you connect it. You're saying if you select a taxi for A, you cannot select the same taxi for B and C. Similarly, B is connected to C and maybe D. हाँ, D के लिए भी है, तो C से connected है और D से भी connected है. C is connected to D and E. So यहाँ पे E बना दिए. C is connected to B and D. E is connected to E and F. So E and F. E is connected to E and G. So sorry, F and G. Okay. F is connected to G, only G, and G is connected to H, and H is connected to I. Okay. So this is the graph. Now the question is color this graph. जितना भी color हुआ, मान लीजिए you can color this graph with 3 colors. मान लीजिए for example, or 4 colors maybe. So you can say that this requires only 4 taxis. Is that all right? Is it all right? Okay. So this is a scheduling problem. Similarly, if there are allocations of CPU, so you will know that how many number of CPU cores you require, because you can think of this as um, processes in a computer, and these are the demands of the processes. Yes.
I don't know, but I doubt your video and the screen is stuck. Means, Sudeep sir, is it the same with you also?
So actually,
Yeah,
yes, sir.
to me it is visible applications of graph coloring, and previously what the taxi you were showing by red color.
I'm
It is
writing
I am
right
able
now.
to see. Yeah,
Okay, I think I have got some network issues. Okay, please continue, but I can hear your voice. Okay.
Okay, but I will
You
finish
can
in.
leave the meeting and again rejoin. Sometime used to get repaired.
But I will finish in 2-3 minutes. So
Okay.
okay. So you can think this as a CPU processes, and then you can obtain how many CPUs are required. Frequency assignment. So you see, when there is some telecommunication networks and two networks are very close to each other, then you cannot assign the same frequency to the both of the networks. Otherwise, there will be interference. So therefore, this graph coloring problem can come into picture. If two networks are very close to each other, then you can make it an edge between them, and you can say that both the towers cannot have the same frequency. Circuit boards. So this circuit boards are actually made into layers, one layer at a time. And what happens is, when you have some circuits in a layer, there may be cases when this circuit can have the same location as the circuit in the above layer. So you cannot print the same circuit in the same layer. You can have multiple layers. So in that application also, you can use this graph coloring problem. Each layer is a node, and the adjacency of one layer with the other gives the edge. Okay. So yeah. So Sudoku we have talked about. We have talked about the Sudoku as CSP, node consistency, R consistency, backtracking, and heuristic we have talked about. This is one Sudoku example I have taken. Another is seat planning problem. So this is a typical problem for, in mainly in America, when they are planning a wedding, they have some number of tables, table 1, table 2, table 3, and these tables, when they invite guests, they assign guests to a table. They say that you have to sit on table 1, you have to sit in table 2, and these guests can have preferences. So guest 1 may not be very friendly with guest 2, and he may prefer of sitting in different tables. So what you can do is you can make these guests as nodes, and the domain will be table 1, table 2, and table 3 for all the guests. And if there is an edge between one guest and the other, that it says that both the guests cannot be seated in the same table. There can be other constraints as well, like if some guests are a family, then they must sit in the same table. Some constraints can be added, and this can be formulated as a not traveling system problem, sorry, constraint satisfaction problem. Okay. Exam scheduling. So this is the same problem which I took from the Harvard University's course. It is same. I have written everything same. Okay, some applications of Sudoku. So yeah, you can read these applications. Okay, so applications of constraint satisfaction problem. So timetabling and scheduling, we talked about how to assign exams. So when we perform timetabling of exams, we have some constraint that if a student has taken two different subjects, those exams cannot be on the same time, it cannot be on the same day, and there are other constraints also. So scheduling of exams, meetings, and other events that can have conflicts. Resource allocation. So we talked about this taxi one, that is a resource allocation problem. You can think about machines also. We talked about CPU. So those are also resource allocation problem. Puzzle solving, Sudoku, crossword logic puzzles. Seating arrangement. So this table problem which we talked about was a problem on seating arrangement. Graph based problem, graph coloring, and other problems. Frequency assignment. We saw one example of graph coloring on frequency assignment. And in decision making, robotics, and many other game applications, we use constraint satisfaction problem. So yeah, this is the idea of today's lecture, and I don't have anything else. Any questions or doubts?
No.
Okay, so next class will not be on Sunday. It will be on Saturday. I will make an announcement in the WhatsApp group as well as in classroom, because I have to leave on Sunday, and there will be no class for the next 2 weeks. I will inform everything in the group. Okay, so please remember to join on Saturday and not Sunday at 6 p.m. We will start machine learning. So this is the end of optimization. Okay, thank you. I'll end the meeting now.